Okay, moving right along, here's problem 2, where we have our little square of stuff, and we want to find the force on mass 5 in the middle. Okay, so let's see if I can do the copy and paste here. And yes, it works. Fantastic. Okay, so we have these 4 masses here, M1, M2, M3, and M4. I happen to know that basically with everybody's numbers, no matter what, you are going to have M1 equals M4. And that's useful in a minute. So there are going to be 4 forces acting on this M5. And again, what I want to do here is instead of using the whole equation where you do like F equals G M1 M2 over R squared times R hat. What I'm going to do is instead I'm just going to look at the magnitudes. So I'm going to go like F equals G M1 M2 over R squared. Find the magnitudes and then worry about directions when I finish. Or actually, I'm going to worry about directions first and then find the magnitudes, and you'll see what I mean. So there are going to be 4 forces, 4 different gravitational forces acting on mass 5. One is going to be towards M1. I'm going to call that F1. One is going to be towards M2. I'm going to call that F2. One is going to be towards M4. I'm going to call that F4. And then we got one towards M3, which I'm going to call F3. And these are all vectors, of course. Now, this is a square, right? And there's some side length to the square. I'm going to call that D, I think. So actually, I'll do that in black. Okay. So D is the length of the square's sides, and that's given to you in centimeters. You have to convert to meters. But anyway, so the first thing we're going to notice is because this is a square, this is all symmetric. This is in the middle of the square. F1 and F4 are the forces going towards mass 1 and mass 4, right? Well, these have the same masses, right? So they're going to both exert the same magnitude of attractive force on M5. And since these are going in exactly opposite directions and have the same magnitude, they're just going to cancel out. So we can take these and just get rid of them. Okay? And then all we have to deal with is F2 and F3. So what I'm going to do first is I'm going to calculate the magnitude of these. So the magnitude of F2 is going to be capital G times M5 times M2 over this distance between M5 and M2. I'm going to call that R52 squared. But what we can see here is because this mass here is exactly in the middle, it's got a displacement here that's d over 2 to the left of M2 and d over 2 below M2. So we take those, square them, we get, to find the length or the distance between M2 and M5, we do Pythagorean theorem, and so we're going to say R, or we'll say R squared really equals d over 2 squared plus d over 2 squared, which is going to equal, this is going to be d squared over 4 plus d squared over 4, so it's going to equal d squared over 2. So R squared equals d squared over 2. So what this F2 is really going to equal, the magnitude of it, is going to be G times M5 M2 over d squared over 2, which means we're going to have d squared and then 2. This is the d squared over 2, and the 2 comes out, of course. Okay, so that's F2. By similar logic, we can find that F3, which is the force that 3 exerts on 5, is going to be equal to, and these are just magnitudes here, so we're not worrying about directions, we're just doing magnitudes. Directions, directions don't count, just magnitudes. 2G M5 M3 over d squared. And so then, the situation we've got here, let me just redraw this a little bit. So we've got, there's our M5, and if we do a free body diagram on it, then what we have is we have this F3 going 45 degrees above the horizontal there, or that's F2 going that way, okay? And then we have F3 going 45 degrees below the horizontal in exactly the opposite directions. So we can actually cancel some of these out, and we can say instead of having 2 forces here, we can find the net force between these 2 and just apply the 1 force. So what we can do is we can translate this into, and we're going to, sort of by convention here, we're going to say that F2, we're going to decide our convention is that F2 is bigger than F3, so that if we take F2 and subtract F3, then it's going to go that way. But you know, even if F3 is bigger, that just means this force would be treated as though it has a negative magnitude, which it can't really have, but if we do the math this way and apply our negative magnitude, it's just going to turn into a vector that way. So either way we're covered. Even if F3 is bigger than F2, the math will come out right. Okay, so what is this F2 minus whoops, okay, what is this F2 minus F3? And that is going to equal, let's see, so that's going to be, we can take the common parts, right? The F2 is 2g m5 over d squared, 2g m5 over d squared. So this is going to be 2g m5 over d squared. All of this times m2 minus m3. Whoops. Yep, I ran, oh, actually I already ran off the edge. So let me take this and just move it a little. Yoink. There we go. And then move that down. I'll just do that down here. Okay. Probably should just redraw the whole thing. F2 minus F3 equals this times M2 minus M3. Okay. So that'll give us our whole magnitude there. And then once we have that magnitude of this force, how do we resolve it into a vector? Well, this we're going to call this, you know, F net. And so once we've got this F net here, we need to resolve this into a vector. Well, so the vector F net is going to equal its magnitude, which is the scalar here we just calculated. So this here is F net, is going to equal this magnitude of F net times a unit vector pointing in its direction. Well, this is a unit vector pointing up at a 45-degree angle, right? So I think you can probably remember from sort of, you know, geometry that if we take the sine and cosine and multiply them each by I and j, we'll get our unit vector. So our unit vector here is radical 2 over 2 I hat plus radical 2 over 2, that's a plus sign there, j hat. Okay? So what that means then is if we take this expression for F net here and plug some stuff in, then what we're going to get is F net equals, this is going to be, so we're going to take this whole expression, I'm going to hold the 2 out for a minute, and you'll see why why in a second. So capital G times m5 over d squared times m2 minus m3, and then this 2, which we multiply by this stuff, so this is going to be radical 2 I hat plus radical 2 j hat. Okay, so let's find out what this is going to be here. And hold on a second. Okay, so we're back here. So our M2 minus M3 is going to be 2 kilograms, or 2 grams. And this is going to be 0.02 kilograms. This is, of course, going to be good old G, 67 E minus 11. M5, I believe we said, or we knew, was 2.4 grams. Oh, so 2.4, 0.0024 grams. And the d squared, d is going to be, let's see, d is 25 centimeters. So it's 0.25 meters squared. And that should get us where we want to go, if I'm not mistaking anything. D squared, boy, is that right? Yes, it is correct. Okay, so let's hope I've got this right, and then this goes times, you know, radical 2 I hat plus radical 2 j hat. So let's plug this in and see what we get. So this is our capital G we already had defined, times 0.0024 divided by 0.25 squared times 0.002, is that right? 0.002 kilograms times square root of 2, and that is going to be our I hat and j hat components. Let's try plugging that in. 7.24 e minus 15. Let's see, 7.24 e minus 15. Yep, and then because it was going, you know, in the diagonal direction, we have, oh, I think I wrote 2,5 instead of 2,4, but either way, it's correct. Because it's going in that diagonal direction, they're going to have the same, the same component, or the component in the y direction and the x direction can be the same. So there you go. That's the answer to number 2.